What range of k wave vector is physically significant for elastic waves? So only those in the first brilliance zone. The range of independent k is specified by k is greater than pi minus pi by a and less than equal to pi by a. What is Van Hove singularity? So in the plot of um this density of states, uh, there are points which have group velocity equal to zero. So d omega versus omega. The critical points produce singularities known as Van Hove singularities in the distribution function here. Density of state of function of as a function of frequency for a Debye solid and actual crystal structure. The spectrum for the crystal structure omega square for small omega but discontinuous develop at singular points. So those singular points are Van Hove singularities. What is Keldysh effect? Okay, not let's go there. Let's go there. What is Keldysh effect? So it's either this, the exciton concentration is sufficiently high over this 10 to the power 3 per centimeter cube of 2K, most of the excitons would condense into a drop. The drop lifetime is 40 microseconds, but the strained GE may be so long as 600 microseconds. Within the drop, the exciton dissolves in degenerate Fermi gas of electron and holes with metallic properties. This state was predicted by Keldysh. So this might be it, or or this the Franz Keldysh effect. It is a physical phenomena that describes how an electrical field affects the absorption of light by semiconductors. The electric field destroys the material's band structure, which changes the joint density of states in conduction and valence band. This results in oscillation of absorption coefficient above the band gap and exponentially decay tail below the band gap. Characteristics क्या है? Broadening of absorption edge, oscillations in continuum part of spectrum, redshift absorption edge, presence of absorption tail for band to band transition. Question number 3. If there are two atoms per primitive cell, then how many optical acoustical branches are there? Here is the answer. If there are p atoms of the primitive cell, then there are 3p branches, two dispersion relations, three acoustical branches, and 3p minus 3 optical branches. So if it's 2, then 3 into 2, that's 6 minus 3, that's 3 optical branches. Okay. So 1 La, 2 Lo, 2 Ta, 2 To. Okay, draw the dispersion curve of polaritons. This might be it. Omega versus K. This is omega T in the middle. That's 1. This is omega L. एक लिमिट रहता है ये एक लाइन फोटोन लाइक इस तरह में सॉरी फोनॉन this line represents omega equal to ck by under root epsilon infinity. That's probably some limit. Real values of k is these lines, and magnitude of k when k is imaginary here. Omega t are these 10 to the power minus 14 radian per second. What does that mean? So here, what are the factors associated with the formation of polaritons? So for the formation of polaritons, it takes at place at low values of the wave vector in comparison to the zone boundary, because the crossover omega photon is equal to ck photon is equal to omega phonon to 10 to the power 13 per second. That's hertz. uh, K is equal to 300 per centimeter. So what is small k? ठीक है, coupling of resonance of photon, this photon coupling entirely, ये वाला होता है यहाँ पे प्लोरेटॉन. ठीक है, what is Davidoff splitting? The Frenkel band, exciton band is doubled when there are two atoms in the primitive cell. The splitting between the bands at k equal to 0 is called Davidoff splitting. Again, what is k? What are dangling bonds? Here, a dangling bond is an unsatisfied valence on an atom that is immobilized. It is also known as immobilized free radical because of its chemical and structural similar to free radical occurrences. Dangling bonds are commonly found in solids with unpaired electrons. They can occur at surface of crystal. So yeah, this surface of crystal when periodicity of crystal lattice is interrupted. Dangling bonds play a role in crystal growth, can lead to anisotropic growth of nanoparticles, tend to capture electrons to complete the bonds, can contain one, two, or no electrons. With two electrons have energy close to valence band of material, while those with none have an energy close to conduction band. What is the difference between large and small polaron? The electron associated with large polarons moves in a band, but the mass is slightly enhanced. These are polarons we have discussed above. The electron associated with small polarons spend most of its time trapped on a single ion. At high temperatures, electron moves from site to site by thermal activated hopping. At low temperatures, the electron slowly through the tunnels slowly through the crystal, as if in a band of effective large mass. Okay, what is the difference? What are the difference between Montvenier and Frenkel excitons? So the main difference between Frenkel and Montvenier excitons are their size, binding energy, and where they are found. Size. Frenkel excitons have a radius similar to interatomic distance, while Montvenier excitons have large radius that extends over lattice constants, many lattice constants. Binding energy. Frenkel excitons have binding energy of 0 to 1 electron volt. Location. Frenkel excitons are uh, often found in insulators or organic semiconductors, while monoclinic exciters are only found in inorganic semiconductors. Dielectric constant Frenkel excitons have a relatively small dielectric constant. Montvenier excitons, the relative motion of electron and whole crystal covers many unit cells. अच्छा से move करता है ये. Localized state. Frenkel excitons become localized and resemble atomic excited state. Montvenier excitons and electron excitonic bonds can be overcome at room temperature. Montvenier का overcome कर सकता है. It's weak. Difference between what is the difference between Brillouin scattering and Polariton scattering? So here, in Raman scattering, Brillouin scattering is when acoustical phonon is involved, and Polariton scattering is when optical phonon is involved. Brilliant phonon and Polariton optical phonon. Brilliant acoustical, Polariton optical. Yeah, makes sense.